All right, let me start out this video on section 9.3 with a comment on problem 9.3.4. 9.3.4 was a fill-in-the-blanks proof of this proposition. And this proposition states that if G is any element of a group G, little g is any element of a group big G, then the inverse of little g is unique. Now, it is important to realize that this must be proved. Just because we typically write G inverse doesn't mean you can automatically assume there's only one possible value for G inverse. That's a common problem, is assuming too much because of suggestive notation. But this is something that needs to be proved. I'm not going to go through the details because there is an outline in the book and you just fill in the blanks. Try to understand step by step what you're trying to do. You're trying to show there's only one inverse, so the way to show that is you assign two different numbers for inverses and show that those two, I'm sorry, I said that wrong. Assign two different letters for inverses and show that those two different letters actually must denote the same thing. So for instance, you could say, let H and K be inverses of G, and then you'll show that H equals K. That means that G has only one inverse. So you can go through the proof and see how that works. All right, next one I'm looking at is 9.3.12, and you should add this on your submission that the problem statement is incomplete. What it should say is, given a group G and A and B elements of G, prove that G is abelian if and only if AB inverse equals A inverse B inverse for all A, B, and G. All right, you can't just show that G is abelian if this is true for one pair A, B, and G. This has to be true for all pairs A, B, and G. All right? So in order to prove that this exercise, you need to prove two things, because it's an if and only if. So you have to prove implications both ways. The first thing you'll have to prove is, given AB equals BA for all A, B, and G, then CD inverse equals C inverse D inverse for all C, D, and G. Now, why did I use different letters C and D? Because you want this commutative property to hold for all A and B. When you do the proof, you can, and you're trying to show trying to show this other property, the A and B here may not be the same as the A and the B in your commutative property. Now, this is not a problem, because if you show that this is true for all C and D, then I can call C, D, or A and B orange apple. It doesn't matter. The important thing is that you're showing this property for all elements of C and D. Again, I'm using different letters C and D because when you actually prove it, you're going to be using A and B in different roles with respect to C and D. Now here it says use proposition 9.3.6, and all this proposition 9.3.6 says is, it says that AB inverse is equal to B inverse A inverse. Okay, for an if the group is abelian. No, actually that's not true for abelian. That's always true for any group. For any group. Okay. So for any group, I can write down this relation, and you can cite proposition 9.3.6. Now, that's not what you want to prove. You want to prove that AB inverse equals A inverse B inverse. All right, so what you should do is start with CD inverse and write down what CD inverse is as a result of proposition 9.3.6, and then say, let A equal blah, let B equal blah. And then by the given, then you can draw a conclusion and get your result. Okay, let me say that again. You should start with CD inverse. Use this to get what CD inverse will be equal to. Then let A equal something, B equal something, and then draw a conclusion that enables you to derive CD inverse equals C inverse D inverse. All right, so the part 2 of this is going to be a similar kind of thing. Part 2 says that given the second condition, given that AB inverse equals A inverse B inverse, you want to go back and prove that G is abelian. What does abelian mean? It means that any two elements commute, again, I'm going to use different letters for those two arbitrary elements. So you're given this condition, and you want to prove that CD equals DC for all C and D in G. So again, we're going to use some kind of substitution. Here I'm going to actually tell you what the substitution is that you want to use. You can let A equal C inverse and B equals D inverse. Okay. Then you can use this given and use substitution, plug in C inverse and D inverse, and then use these two propositions, and then you can use that to show that CD and DC are both equal to the same thing. All right, so you're going to find a way to show that CD and DC are both equal to the same thing. All right, and that will show you that CD equals DC. Okay, so let's look at 9.320. 9.320 says, given a group G and two elements A, B, which are elements of G, prove that if G is abelian, then any solution of AX equals B is also a solution of XA equals B. Okay, given a group G that's not abelian, show that it's always possible to find an equation of the form AX equals B, which has a solution that is not a solution to XA equals B. So I'm going to leave the first part to you, who shows that any solution of AX equals B is also a solution to XA equals B. So let me do the second one, which is the case where G is not abelian. So suppose G is not abelian, then that means that there must exist a pair of elements in G such that AC is not equal to CA. Because abelian means that this product and reverse product are always the same. If it's not abelian, there must be some product AC that is not equal to CA. So what you're going to do is define B as something, and then you'll have something is a solution to AX equals B, but something is not a solution to something else. All right. So here, kind of give you some hints on how to fill this in if you want to use these hints. If you want to do it yourself, that's fine. But this is one way to do it, is just by filling in its outline. Your writing shouldn't be that much more than this. Okay, this gives you kind of an idea of how complicated this problem is. Okay, for 9.322, I'm not going to say too much about this. It says to prove proposition 9.321, we need to prove both BA equals CA implies B equals C, then AB equals AC implies B equals C. Why do these two statements require two different proofs? It is important not to assume anything. So here we would just say, since the group is not necessarily commutative, we can't assume that BA equals AB and CA equals AC. So if you prove something about BA and CA, that doesn't say anything about AB and AC. So when you see this kind of question, this is the kind of answer that I'm looking for. Now, exercise 9.3.24 relies on this definition, and you're defining the nth power of a group element and the minus nth power of a group element. And so we have g to the 0 we define as the identity element, but for positive integers we define the g to the n as g operated on itself n times, g to the minus n as g inverse operated on itself n times. Okay. So you see that we can't just automatically define g to the minus n. We have to define g to the minus n in terms of the inverse of g. All right. So using this definition, we want to prove that the inverse of g to the n is g to the minus n. Okay. This also is not automatic. G to the minus n is n copies of g inverse. Gn inverse means you take g to the n and then find some element that gives you the identity when you multiply. All right. So what you're going to need to do is show that this g minus n satisfies the inverse property for gn. In other words, if I take gn and take this g minus n, I should get the identity. Also, if I take this g minus n, operate on gn, gives me the identity. So that's what I've done down here. So I kind of outlined it for you so you can fill in the blanks. All right, so you can see where the blanks are. So here you have g. So this one is this is actually going to be n times, right? And this is going to be n times. Okay. And again, so this is just rewriting. This is just substituting those results. And what I'm doing here is I'm reassociating this product. Now, because of associative law, you can put parentheses wherever you want. Now remember, this is going to be G's here. This is going to be G inverses here. I can reassociate this so that I just have these two inner ones together in the same group. So that's what I've done. Then you need to think about what's left over here, what's left over here. Okay. And then what happens to GG inverse? Well, you use the inverse and identity property to figure out what happens to that GG inverse. And then how many times left? Here you have something a certain number of times. Here you have something else a certain number of times. How many times do you have this? How many times do you have that? So what you're going to do is you're going to outline the process of reducing this expression down to the identity. Okay. So you start with Gn times G minus n, and you reduce that to the identity. Then for the other way, you can just say something like this. Okay. Okay. All right. So now here you can write this out. You can start writing this out the same way, and then just say, applying associative, inverse, and identity, how many times you need to apply these three properties as above gives us G inverse, G minus n, Gn, and of course you want that to be the identity. Okay. All right. So you're showing the identity property both ways. I'm sorry, you're showing the inverse property both ways. The second way is similar to the first, so you can just kind of give a brief outline of how you do the first one. All right. So that's how you can take care of that problem. Now, 9.326 is kind of long. 9.326 is asking you to prove parts 2 and 3 of proposition 9.325. And I think you're actually going to need separate pages for these two proofs. The reason is that in order to prove these, you really need a bunch of cases. The thing is that when you have a positive integer and a negative integer, then the definition of g to the m is different when m is positive integer and when m is a negative integer. So you're going to need separate cases, and in fact I've given you all 5 cases. The first case is well, we're looking at 2 here. G to the m to the nth power equals g to the mnth power. So there are 5 cases. The first case is that m times n equals 0. Second case, m and n are both greater than 0. Third case, m is greater than 0, n is less than 0. Fourth case, m less than 0, n less than 0. And fifth case, m and n are both less than 0. Now, the first and second cases you can get pretty easily. What you're going to do in the first case is you'll actually show that both sides are equal to the identity. So mn equals 0. That means that m equals 0 or n equals 0. So if m equals 0 or n equals 0, you can show that both sides will be equal to the identity. Now this case, when mn is bigger than 0, you can just write it out that so I'll just write it up here. You can write something like this: g to the m to the n is equal to g, and then this is going to be m times, and then you're going to do g, this is m times. And then all together you're going to do this n times. So how many g's do you have? All right, so you think about that, and that will give you this second, that will give you property 2 here when m and n are greater than 0. For the other ones, you're going to use this second one, but you have to take care of the inverses. For instance, if m is greater than 0, n is less than 0, how am I going to write g to the n? Well, what you have to do is think about this, that if n is less than 0, then n is equal to minus the absolute value of n. Okay? N is equal to minus the absolute value of n. Now, then I should write g to the m to the nth power as g to the m to the minus absolute value of nth power. Now we have a definition for how you raise a group element to the negative of a positive integer. And that's what we have here. That group element raised to the negative of a positive integer is that group element inverse to the positive integer times. Okay, so we're defining this quantity in terms of the inverse of the group element. Okay, that's the definition that we saw in the previous problem. Just go back and see. That was this property here. Gn inverse equals G minus n. So we're starting on this side and showing that it's equal to, and making it equal to this side. All right, so I've changed this to bring the inverse inside. Now, what about this group element to the m to the inverse power? Well, I can use the same proposition the other way to show that's the same thing as G inverse to the mth power. All right. Now what do I have? I have m is positive, n is positive. I can use, m is positive, absolute n is positive. I can use property 2 to combine these two exponents into a product. Okay. Then what do I have? I have G inverse to a positive number. But using the definition of G to the minus k one more time, G inverse to a positive integer is the same as G to the negative of that positive integer. But then we have the minus back with the absolute value of n, so that becomes n again, and we get Gmn. All right? So you can work through 4 and 5 in a similar way. All right? So if you have one of these negative numbers, then you have to rewrite it as negative of the absolute value of that number. All right? So that's all of the problems for 9.3 that I'm going to look at.